Hey guys, it's Jair, and today I'm going to be showing you guys some of the performance metrics of Abendigo and also talking about the way that I achieve these performance metrics. So for the first test, I'm going to enable system.gc suggestions every 8 seconds, and I'm going to show the footprints of the process inside Windows Task Manager. So let's run the cheat. Process ID is 10868. So that is 10868 right there. So you can see that the footprint is roughly 112 megabytes to 130 megabytes. And just give it a few seconds for the JVM to warm up, and we'll see the actual results. So I believe the JVM is already warmed up, and you can see our memory footprint is right under 114 megabytes. And CPU usage is between 0 and 1%. And of course, this is with CSGO running and Camtasia recording. So you have to take that in consideration as well. So 0 to 1% CPU usage, and we are only at 113 megabytes of memory footprint. So let's dig deeper, and let's open up a let's move CSGO out of the screen, and let's open up JVisualVM. This is my last run, and we're going to profile this process. And let's see, what is it? 10868. So just so you guys can see, you can verify this is the process, and you can see the JVM flags. There are none. So see that. This is with the default XMX256, and this is the default arguments on a server class machine. I am forcing to use G1GC, which is garbage collector, because this is going to be the default garbage collector in Java 9. Also, we can take a look at our Visual GC reports. This is a plugin for JVisualVM. You can see that it reports only 290 milliseconds of pause in total across all these 18 collections. Now it's 308 across 19 collections, and you can see the last cause is pretty much always going to be system.gc, because we suggest that it GCs every 8 seconds. You can also see the eating space ceiling is only at 1 megabyte, 5 megabytes now. So you can see it's really great so far, and you can also see the eating space times are only 6.4 milliseconds. So most of the time was actually spent on the old gen collection, which is that's actually good. It's really good for us, because then most of our guys are going to end up in the old gen, and we won't have to collect very often because that pool is a lot larger. So let's go and look at our buffer pools tab. So you can see here there is around just slightly over 80 megabytes of used memory, and you can see there's only actually 7 total buffers. So most of this memory use is actually from the actual client.dll and module.dll, or sorry, client and engine.dll modules, because we read the entirety of them in order to do offset and netvar scanning. The rest of them, which maybe is five different types, are buffers as a result of all this functionality. So I'm going to show you guys, of course, how we actually save on creating byte buffers, and I do use direct byte buffers for all of this work. So there are no on-heap buffers going on here, which means that we get very fast access to native memory, which JNA loves. So let me show you guys that in just a second after we profile the actual memory to see what kind of garbage is going on, because there is very minimal, but there is some. See, right off the bat, we don't really have any reports here, but you can see that the hash map entry iterator is climbing. Now, the reason that we have so many entry iterators is because of our ESP plugin right here. And you can see that every 64 milliseconds here, we go through the current object count, which is anywhere from 64 to 128, I believe, on a lot of public servers. Right now it's 64. And For each of that, we go through all of the players in existence, which there's typically 10. Typically 10, well, at least in my game, there's only 10. So if you think about that, we're going through this 640 times per 64 milliseconds, which is a really big deal. That's a lot of iterators that we have to create. Each time that we do this iteration, it creates a new iterator, and that's where that hashmap entry iterators come from. Hopefully in the future, I'll be able to replace the existing hashmap with not only a thread safe, but also a garbage-free hashmap, or I might just make my own. Until then, we're just using regular hashmap, and we fall to the fault of concurrent mod exception right here every once in a while, which I don't think is worth the trade-off of using concurrent hashmap, which creates even more garbage, much more garbage. Just a tip for people using concurrent hashmap: if you want to have a garbage-free environment, do not use it, because it will make an entry upon each put, which is not good. Actually, upon a lot of sets as well, if it wants to use non-blocking mode, which is really unfortunate. I would like something that is non-blocking and creates no garbage and thread safe, but I don't really think there's anything out there until I make it. So until then, this is what we have to do with, and it's not that big of a deal. So let's switch over to the non-GC selected, or GC suggestion, which is going to have a higher memory footprint, but the overall system is going to be much more efficient. Not really efficient, but much more stable and more to the liking of the JVM. So the JVM really good. It's really good at optimizing itself, and because of that, we are going to have what I would consider a much better system than if we were to suggest that it garbage collect every 8 seconds. So let's run it. Okay, so we're at process 10160. So let's monitor the footprint 10160. So you can see it's significantly higher until the JVM settles a little bit. You could see that we had quite some high CPU usage. We're still getting a little bit of high CPU usage there. But until the JVM settles, once the JVM settles, you can see that already. I believe it's settled already on server class. Once it settles, it's extremely consistent. So you see it's just around the XMX, and slightly a little bit under there, and still doing some warm-up tasks, and it's not very bad at all. I mean, nowadays, I, for example, have 16 gigs of RAM. A lot of people out there have at least 8 or 6. So, all things considered, memory is a good trade-off for pause times and for CPU usage. So, let's actually look at the profiler, and we're going to see what it's actually doing right now, which I do have an idea of what it's doing. So you can see the same parameters and everything going on here. G1 GC, no JVM flags, and server class, 64-bit server class. So let's go ahead and actually look at the visual GC, which is really indicative of what's going on right here. So you can see, look at our pause times in comparison to the last time. Last time we had, 400 millisecond pause times already with about 18 different collections. Now our pause time total GC pause time was only 4.8 milliseconds, which means we only spent 4.8 milliseconds in garbage collection. The entire rest of the time was dedicated to the cheat working and, aimbot, ESP, bunny hop, all that stuff. The rest of the process was dedicated to that. Very similar to the performance metrics you get out of C++, and perhaps even better. So you can see that's very nice. Another thing, you can see that our ceiling is quite high for the Eden space, but once we reach that ceiling, you're going to see how much it drops down. Just before it runs the next collection, I want to show you guys the buffer pools. So notice something here. The count is 186. Why? Right? Why do we have so many byte buffer objects? Well, it's because we do the netvar scanning and pattern scanning, and we have all that stuff in memory, and we have yet to collect it. Meanwhile, in our other case, every 8 seconds we collected it. So it already, oh, there we go, it just collected. So it had already been collected in the other case. But now, we had that 186 byte buffers still awaiting to be collected. Now that it finally collected, you can see the count's only 7. And in Visual GC, you can see there's basically 0 garbage, which is incredible. And you can see the last pause only took maybe 5 milliseconds or 6 milliseconds to actually perform. So you can see just how efficient G1GC is. You can see just how efficient the JVM is when it comes to handling a low garbage workload. So now you can see we have only around 10 milliseconds total pause time with only 3 total collections through all of this functionality that we have in the cheat going on as a result of the way that I programmed the cheat. I designed the cheat. So now that you guys get the performance metrics, I'm going to show you guys some actual code to see what I did to achieve this kind of performance at the JVM with a pure Kotlin code base. So let's just minimize CSGO so I don't get distracted, and I'm going to minimize this as well. Let's get CSGO out of the way. All right, let's close out Abendigo as well. Just closing all this stuff. Just give me a sec, guys. I wanted to. There we go. Okay, so let me just move CSGO a little bit so you guys don't get distracted. So the first thing that one of the main constructs of Abendigo is this little class here called Updatable Lazy. And Updatable Lazy was my idea. It's my framework for how a cheat with plugins that are very modular and very separated should work. So basically it's a framework so that you can define a value and you're able to update it when you want, or you're able to not update it if you don't want to update it. So it gives the plugins a lot of control. So let me show you some different operators. So the base operator is invoke, which is called like this. Let me show you guys an example. It's called like this without any numbers inside there. That's just an invoke, and what that means is it just gets the current stored value inside the updatable lazy and returns it and doesn't do anything else. It doesn't update. It just checks the last value and returns it, which is basically free. So let's talk about the second thing. You can see this is a unary plus operator. The unary plus is an update call, which means force an update and return the new value. So you can see if I go here, you can see it's actually redirects to the update method, and it calls the initializer, the lazy initializer, sets the value to that, changes the update stamp so that we can record the time, and returns the value. Finally, which you have seen here, we have invoke with a duration. Now the default duration's time unit is milliseconds. So by invoke with duration, I mean what this means is get glow object if it's been updated in the last 64 milliseconds. If it hasn't been updated in the last 64 milliseconds, update it and then give me the value. So this is a really nice construct because a lot of plugins can really improve the performance in this way. And it lets all the plugins be so separated, the code base be so modularized and separated, yet you're still able to achieve excellent performance because of this updatable lazy system. So you can see right there, that's how you do it. And if, for example, you wanted to only update every 1 second, you could, for example, do that. And there you go. Now, if it was updated in the last second, I would like to update. So you can see that's very nice and convenient. And you can see because of Kotlin providing these operator overloads, the syntax is really nice and really boilerplate free. So let me talk about what else I did. Something else that I did. Let's see. Trying to think. Oh yes. So one enormous performance beneficial feature is actually not in Abendigo specifically, but in my library that Abendigo uses called cotmem. And if we check out ContMem's class, I was actually working on it a little bit. If we check out ContMem, the main file, we can actually see the pointer caching and byte buffer caching system. So first of all, for pointers, it's very simple, very easy. All I do is I use one pointer per thread, and Java makes that easy with thread locals. One pointer per thread with default p of 0, and we simply get the pointer for the thread, and I reuse it, and then I set the native value to the address, and then return that pointer, and then use the pointer immediately. Because of the updatable lazy design, and because of the way that ContMem is designed, it doesn't matter that it's unsafe to do this, because everything is locked at in a global lock called ContMem lock. It's up here somewhere, ContMem lock. So it's actually safe to do this, and we always have the right values. We never have the wrong values, even for writing and reading at the same time, because it uses the same global lock to do both of them. So that's the way that I cache pointers. We simply only have 4 pointer objects if we had 4 total system threads that were accessing pointer. So there you go. Then the major caching for byte buffers is simply a hash map, and with the hash map we have a type, and that's the class type. In Kotlin, in Java, this is equivalent to class of any. In Kotlin, uses the asterisk symbol. We just map the type to the byte buffer. So we only have 1 byte buffer per type. So for example, if you want to read an int, it's just reusing that exact same direct byte buffer over and over and over, kind of like pretty much exactly how we did with the pointers. So we use that byte buffer that's already allocated in native memory and super fast for a JNA to use in the native call, and we do the native read or write with that buffer, and we get our results back in a Java heap form, and that's it. And then we just, next time we use it, if it was already cached, we clear the buffer each time, because byte buffers are designed with no garbage creation in mind, and we simply reorder it to the native order, and we're good, and we just reuse that same buffer. That's the way it works. And another case that I use for caching is cache it, instead of by type, by size. And this is used for our net var scanning in order to really reduce the amount of garbage and the amount of garbage, the amount of retention that, that our byte buffers have. So with this system, I simply cache by the amount of bytes to read. So on multiple usages of the same common amount of bytes, it's just reusing the same buffer, because it doesn't matter, because it's safe. Like I said, it's safe to do this because we have a global lock and everything. So I can't really say anything else. That's it. You can see I was also working on this cool map cache method, but I was having problems and performance concerns with the pair garbage creation. So hopefully Kotlin will be able to inline pairs in the future, because that would be really cool as well. But until then, I don't think I'm going to be using it, because I had some performance issues with creating pairs on each read and write, which is terrible. So I mean, other than that, let me just go into one more thing with ContMem. One last final thing. Okay, so let's open up process, and let's see how we actually did our magical reading and writing. So simply put, when you have an inline function in Kotlin, you can reify the generic type. And that's what I do. I reify t, and then I can use type inference to get the type. And that reified type is passed in as t, and I simply refer to the k class here, and then I simply refer to the Java class like that. And that's the way that I store the cache types over here as keys inside types to buffer. So I mean, it's quite simple, and that's all you do in Kotlin. That's all you have to do, and it enables really, really sugary short syntax. So I just wanted to mention one more thing before we close off. hopefully the Kotlin this Kotlin bug will be fixed. At the current time, you cannot use set or get in operator form for a reified inline method. So if I were to switch this with the actual form, you can see even IntelliJ is telling me, hey, why aren't you using the operator form? Even if I were to switch it to that, which would look like this, which is absolutely beautiful in my opinion, this is what I want to be able to do. Unfortunately, it throws some unsupported operator exception, something like that, in that case. So I'm really hoping and really looking forward to Kotlin fixing this bug, that we will be able to have this very concise syntax. Let me just show you. Let me undo this and let me show you guys the get form. For example, this. For example, I could change into this, which in my opinion is just absolutely beautiful, and I would really like to be able to use that syntax. So hopefully the bug will get fixed in the future. We'll be able to use that syntax in our plugins, and it'll really be nice and really make Abendigo's and Kotlin syntax really sugary and really just perfect to use. But until then, I'm just waiting, and hopefully the Kotlin guys will fix that. I'm really excited for that. That's why I mentioned so much. So anyway, guys, please subscribe and like the video if you like the video. And let me know any questions or anything you guys have in the description. And again, you can support Kotlin by donating to us on our website if you want to. You can also contribute to the project, which is on GitHub, entirely open source. And comment on where I post this, certain threads, if you have any questions as well. So thank you guys for watching, and see you.